Imagine a bustling, high-pressure restaurant kitchen. An incredibly complex dish is being prepared, passed forward down the line from cook to cook, each adding their own specific ingredient before it is finally served. The dish makes it out to the dining room, but the moment the customer takes a bite, they gag. It is overwhelmingly, ruinously salty. The head chef now has a serious problem. Because this recipe involves dozens of intertwined steps handled by a long line of people, looking at the final product doesn't reveal where the process broke down. To find the culprit, the chef has to work in reverse. They trace the steps backward from the final garnish, past the plating station, all the way back to the initial prep cook to figure out exactly where things went wrong. In the world of artificial intelligence, this process of tracing mistakes backwards to fix them is how machines actually learn. It is a process known as backpropagation. An AI making a prediction works a lot like that kitchen assembly line. Raw data moves forward through a series of connected checkpoints, called nodes, until it produces a final guess. When the system makes a guess, we compare it to the perfect correct answer. The exact mathematical difference between the AI's guess and that perfect target is called the loss. It is a strict measurement of exactly how wrong the final product is. To fix this, the system calculates something called a gradient. You can think of the gradient as a mathematical compass. It asks a simple question. If I tweak this specific ingredient, does the final dish get better, or does it get worse? A real AI model doesn't have just 3 or 4 cooks on the line. It has millions, sometimes billions of individual settings, known as parameters, that all need to be adjusted at the exact same time. Calculating the loss and the gradient tells the system that it made a mistake and which direction to adjust. But that alone doesn't solve the problem of figuring out exactly which specific parameters need to change. To do that, the system has to start at the end of the line. The final plater passes the blame back to the sauce chef, who passes it back to the prep cook who oversalted the broth. These formulas show the chain rule from calculus. This is the math that allows the system to step backward, linking every individual's action to the final failure. Because this error signal travels backwards step by step, every individual node learns exactly how much it needs to turn down its own personal salt dial, which we call the network weights. The kitchen then makes the dish over and over again, thousands of times. Every single round, the system slightly adjusts those dials to constantly minimize the error. This looping process of walking down the slope of the error is called gradient descent. Without this method, the network would just be spinning billions of dials at random, hoping to stumble onto a better result. That would take millions of years to get right. The true efficiency of backpropagation is how it distributes the exact mathematical fix to every single parameter in a massive system, all in one smooth backward sweep. This diagram displays a computation graph for a neural network. Dissolving the kitchen metaphor, cooks and ingredients are actually digital locations passing data. The recipe steps are large groups of numbers layered together, passing through decision filters that determine what reaches the final loss calculation. This slide highlights the actual math of backpropagation at the bottom. The backward pass calculates exactly how much to tweak each of those settings, updating the rules for the next round so the model gets smarter. This document is Paul Werbos's 1990 paper detailing backpropagation through time. It shows that an artificial neural network is essentially a digital assembly line constantly refining its own instructions, a deeply established scientific concept. This exact architecture, scaled up to massive proportions, serves as the foundational building block for almost all modern artificial intelligence. But there is a catch. What happens when our digital cooks find a pretty good recipe and they get too scared to make big changes in case they ruin it? This chart illustrates a loss function as a topographical map. The black path shows a system stopping in a shallow dip, a local minimum. It settles for good enough, completely missing the global minimum, the deepest valley representing the perfect zero-error state. Even with this limitation, when dealing with massive real-world problems, these pretty good local minima are often highly effective and completely practical. When an AI learns to drive a car or write poetry, it is the result of a system relentlessly learning from its mistakes, one backward step at a time.